So let us then start today's session. Okay. Okay. So the first question that we have over here is this question. In the K map shown below, X denotes a don't care term. What is the minimum form of function represented by the K map? So quickly tell me what will be the answer. What will be the answer? See, if we start grouping, then you can see that this is a group of 4. Okay, group of 4 over here we have. Now don't think that we will take something like this. Okay, like this, and then again we are doing like this. No, this is wrong. Okay, this is wrong. So this is one group of 4 and another is this one. Okay, so we can even make a group of 4. Look here. So this this and this. Okay, so for the first group, what is common? So you can see out of AB, A bar is common, and out of CD, so C not D complement is common. And for this corner groups, what do we have? So out of AB we have common B complement, and out of CD what do we have common? So that is C. So which option do we see? A bar D, B bar D. So have I done some mistake or what? Yes. So D complement is common, not C. Okay. So D complement is common. So option A is correct. Okay. Option A is correct. Anybody got option A as your answer? Okay, fine. So over here I had given you some problem or what? This means this I have drawn one K map. So I don't remember exactly what I had asked you guys to do over here. So was it finding prime implicants or essential prime implicants? So I exactly don't remember why I had. Yes.
No, sir. You haven't talked about prime implicants and essential prime implicants, I think.
Okay, so I haven't talked about prime implicants and essential prime implicants. Okay, fine. Okay, fine. So what is prime implicant? First of all, let us discuss what is implicant. Okay, implicant. See, basically this is a function. This K map is a function of min terms having min term number as 1, 5, 7, 12, 13, sorry, 8, 10, 12, 13 and 15. So this is your function. Now let me assume there is one more function which is defined like this. So this is actually what? This is one of the implicant of the function f. Let me assume one more function. So this is one more implicant. So the subfunction of a function are known as what? It is known as your implicants. Okay, it is known as your implicants. Now for example, If we have a function something like this, now this is not implicant. Why? Because this 2, this min term, is not present in the function that have been given to us. So this is not the implicant of this function. Now, what do we mean by prime implicants? So prime implicant are, first of all, they are basically implicants. Okay. First of all, they are implicant. Implicant means what? They are subfunctions. Now, prime implicant, by the term prime implicant, we mean basically we need to find the groups. You need to find the groups without requirement. I should have written all the groups. Now, what do I mean by this? All the groups without requirement. Look over here. So start making all the groups present over here. So one of the group of 4, I can directly see that this is one group of 4. Okay, this is one group of 4. Now our main aim over here, when we are actually finding the prime implicant, is that first of all you need to maximize the group size. First is what? Maximize group size. Next is what? Find all the groups, irrespective of requirement. Look over here. So I have one group of 4 like this. Now I can make a group of 1, a group of 2 like this. Another I can make like this. Okay. Another I can make it like this. And one more like this. See, one thing you can look over here, that this group, see, if I want to write the minimum expression, understand what is prime implicant from here. See, if I wanted to write the expression, minimized expression, I could have done it like this. None of the ones are uncovered. But what I told you, find all the group without requirement. So this is one of the group. This is one of the group. This is one of the group. Now one more group I can make, which is not required, but still it will be counted as your prime implicant. It is this group. This group, see, this is actually prime implicant, but it is not required. Okay, so how many prime implicants do we have? 1, 2, 3, 4, and this is 5. See, this blue color group, it is not required, but still I am considering it as prime implicant. Now you might be getting one doubt, that sir, why didn't you take it like this one? Means, why didn't you consider two group of ones like this, one group like this and another group like this? See, first of all, I told you what? Maximize the group size. Maximize the group size. See, this 4 ones, they can make a group of 4. So first of all, you need to maximize the group size. Now search for all the groups that are smaller than this. Okay, so the maximum group size you can have over here is 4. Now if you had one more one over here like this, then you could have said, okay, we can construct one more group like this, but here it is not present, so we are not doing. So here we have this 4. So first we have made a group of 4. So first aim is to maximize the group size. So we have group size of 4 over here. Then find the smaller groups irrespective of the requirement. Find the smaller group irrespective of the requirement. So this is one of the group I can make. Another group I can make it like this. Another group like this. And one more group I can make a group of 2 like this, which is not required, but still it is considered as prime implicant. Tell me, have you understood the concept of prime implicant? Concept of prime implicant, any doubt over here? So you can ask. So now look, what is essential prime implicants? So first of all, essential prime implicants are prime implicants. Okay, first they are prime implicant, and after that essential. Essential means what? That these kind of prime implicant only have one alternative to group. Okay, only one alternative to group. So search for those one which have only one option to group, or you can say in another language, search for the ones which have only one option. So look over here, this one, I am talking about this one. This one has only one option for grouping, that is to make a group of 4 with this other remaining one. Even this one has only one option to make a group of 4 with this remaining one. But look at this one. This one, it has two options. Either it can go with this group of 4, or even it can go with this group. Okay, so this one is not, means this group is not prime implicant due to this one. But look at this one. Which one? This one. See, this one has only one option to make a group with this one. So this group is essential prime implicant due to this one, not due to this one, because this one has option. Either it can group with this one, or it can make a group of 4. So this is one essential prime implicant. This is one essential prime implicant. Now look at this one. Either it can make a group of 2 like this, or it can make a group of 2 like this. So there are two options for this one to make a group. So this will not be an essential prime implicant. Now look at this one. It has two options. Either it can group with this one, okay, or it can group with this one. So this is also not essential prime implicant. So we have covered this one, this one. Now last is this one. So look at this one. It has only one option to group, and that is what? Like this. So this group is essential prime implicant due to this one, not due to this one. So this is also one essential prime implicant. So there are three essential prime implicants over here. Tell me if there is any doubt understanding what is essential prime implicants and prime implicants.
Sir,
Yes,
hello.
tell me, Srihari.
This essential concept I got it, and but the last, that prime implicant, actually little bit I think I have
Okay,
missed on.
okay, I will explain once again. See, your main task over here is to find implicants. First of all, in prime implicant, find implicant. Now implicant should be such that one, maximize group size, two, maximize the number of group. So your first aim is to maximize the group size, and then you need to do what? You need to maximize the number of group. So first, search for a group of 8, or even group of 16. Group of 16 is not present, then search for group of 8. No group of 8 is present, then search for group of 4. So you can see there is one group of 4. Okay, there is one group of 4. Now remaining, is there any group of 4 present over here? There is
No.
no group of 4 present over here. So next group size will be what? Group of 2. Now find group of 2. This is one group of 2. This is one group of 2. This is one more group of 2. Okay, so you have found out all the group of 2. Now don't go like you are searching for group of 1. Why? You won't be searching for group of 1 because all the ones have been covered, so you don't require to find group of 1 anymore. Okay, if there was a 1 present over here, not over here, means we can still make a group of 2 like this. So there is no position here. No, I cannot put a 1 to make a group of 1, so it's okay. So first condition is what? Maximize group size. So you have done that. Next condition is what? Maximize the number of groups. See, you haven't maximized the number of groups. Why? Because I can make one more group of 2, and that is where this one. I can make one more group of 2. Can we make any more group of 2? Now don't say, sir, we can make a group of 2 over here. No, this is already contained in your group of 4. So if you want to maximize the number of group, you need to find one more group of 4 over here to make one more alternative. You can maximize the number of group size in a group of 2. Okay, did we understand now? Theory?
Yes, sir. Yes, sir.
Okay, any
So
doubt?
then, like, you asked what are the prime implicants? Um,
So prime implicants are, one of the group is M15, another is M5, 7, 13, 15, another will be M12, 13, another will be M8, 12, another will be M8, 10. So there are in total 1, 2, 3, 4, 5, 5 prime implicants, and how many essential? 3 essential prime implicants in this.
so, sir, my doubt is that if we are not considering that 12, 13 and just considering 12, 8,
Okay. See, then you
so
are violating the second condition. Maximize the number of group irrespective of requirement.
okay, so we should not check for redundancy or all those things.
No,
Just
you
maximum.
shouldn't. You shouldn't care about redundancy in prime implicant. See, just try to solve this question. Just try to solve this question. Here they have asked essential prime implicant. First, you tell me what are the prime implicants. How many prime implicants are present over here? Then you tell me what is essential prime implicant. So this question will give you a better understanding. Try to find this one first.
So one quad is there, two pairs,
No, it's
three
okay.
pairs.
You just tell me what are the number of prime implicants in the chat and essential prime implicants. Okay. See, look over here. The K-map for a Boolean function is shown in the figure. The number of essential prime implicant for this function is. So you need to find essential prime implicant. So first, as this is what? This is a 4 variable. So start from group of 16. There is no group of 16. Group of 8. Even I can see there is no group of 8. Second is group of 4. So is there any group of 4? Yes, I
Yes.
can see one group of 4. This is one group of 4. Now, can I make any other group of 4 using this 4 ones? No, I cannot make. So this is one prime implicant. At the moment, we are just discussing about prime implicants. Okay.
Okay.
So we don't have any more group of 4. So group of 4 we have made. and we have maximized the number of group size also irrespective of requirement in 4. Now go to group 2. Group 2, see how many group of 2s are here. So this is one, another is this one, okay, and any other we have, so this one, okay, so there is this only. Okay, so there is no more, you can see I cannot maximize any more over here, okay, irrespective of the requirement also there is no more group. So group of 2, these two are the group of 2, means this one and this one, 3, there are 3 group of 2. So basically what you can see, that the number of prime implicants are how many? 1, 2, 3, 4. So prime implicants are 4. Now let us check essential prime implicant. So look at this one. This one has the option, either it can group with this 4 and make a group of 4, or it can do what? It can make a group of 2 with this one. So this one, due to this one, there is no essential prime implicant. But look at this one, okay, it has only one option, and that option is to make a group of 4 with this 4 1. So this is essential prime implicant number 1. Even this one has only one option, to make a group of 4 like this. So it will be included in this only. This is one essential. Don't say that this is, sir, one more essential prime implicant. No. Look at this one. This one also has only one option, to make a group of 4 with the remaining 3 ones. So this is first essential prime implicant, in which we have covered all the ones. Now look at this one. This one has only one option, to make a group of 2 with this one. So this is one more essential prime implicant. Okay. Check for this one. This one has only one option, to make a group of 2 like this. So this is essential prime implicant 2. Sorry, third. Now look at this one. This one has two options. Either it can make a group of 2 with this, or it can make a group of 2 like this. So this is not essential prime implicant due to this group. But look at this one. This one has only one option, to make a group of 2 with this one. So this is your fourth essential prime implicant. So essential prime implicant 4. Understand that this group is essential prime implicant due to this one, not due to this one. And this essential prime implicant 3 is essential prime implicant due to this one, not due to this one. Okay, so this is very important. So how many essential prime implicant we have? Essential prime implicant also 4. So Srihari, did you understand now what is the concept of prime implicant and essential prime implicant?
Very much clear, sir.
Okay, so now solve this very quickly. So such type of questions will be asked. So you need to find the prime implicants over here. Quickly tell me. Any answers?
4.
4. Okay. So let me see. See the total number of prime implicants for the function. So first is, as this is a 4 variable, so search for group of 16. It is not present. Group of 8, it is also not present. I can see there is one group of 4 over here. So this is one group of 4. Any other group of 4 that I can make? No, I cannot make any other group of 4. So one more. Now let us go to group of 2. So this is one group of 2 I can make. Any other group of 2 I can make? Yes, one more group of 2 I can make like this. Okay. So any other group that I can make? No, I cannot make. So the number of prime implicants are how many? 3. So why did you say 4? Where are you getting 4? How are you getting 4 over here?
I haven't considered the quad, sir. Sorry.
I told you. Now don't consider quad as a group of 2. You cannot do that. First, your first aim is to maximize the group size and then increase the number of groups. So you have already made this a group of 4. Now if you have alternatives for ones, so you can make a group of 4 only. Don't consider this as group of 2 like this one and this one. No, this is wrong. If you have alternative, you can make a group of 4 for this 4 ones, but you cannot make a group of 2. So prime implicants are how many? Prime implicants are 3 over here. So Chetan, have you understood? Okay, next question. This one we have. So any answers? So first of all, you guys need to decode this, that what basically they have asked over here. Okay, what are the min terms? So such kind of question will not be asked in HAL. Okay, directly they will give you actually the minterm numbers. Okay, here you need to find what will be, means where are the minterms, all those things you have to do. But in HAL they won't be doing like this. So first is what? WY. So WY means what? W is equal to 1, Y is equal to 1. Where are the places where W is equal to 1? So these two are the places, and Y equal to 1. Where do we see? Over here and here. So the common are this cell. So all the ones will be present in the common cell. Next is what? XY. So X equal to 1, Y equal to 1. So X equal to 1 is present over, here and here. And Y equal to 1 means it is present over here and here. So these are the common places. So over here also we have one. Okay, fine. Now next is what? W bar X, Y, Z. So W bar X, Y, Z. So this is 7. Okay. So W bar X, Y, Z. So 7 is where? 7 is over here. Okay. So this is already taken. Let's look. 0, 1, 2, 3, 4, 5, 7, 6, 8, 9, 10, 11, 12, 13, 15, 14. Okay. So 7 is already taken. Next is what? W bar X bar Y. Okay. So W bar X bar means over here and Y equal to 1. So where is Y equal to 1? Over here and here. So this ones will also be filled. Next is what? XZ. So X equal to 1, Z equal to 1. So X equal to 1 we can see over here and Z equal to 1 is present over here and here. So the common group are this and this common cell, sorry. And next is what? X complement, Y complement, Z complement. So X complement, Y complement, Z complement. So where can we see X complement? We can see X complement in all this place and this place, and Y complement, Z complement. So this place, so basically this and this is going to be filled. Now you need to find what? Essential prime implicant. So directly in HAL exam, they will give you this K map and they will ask you what is your essential prime implicant. They won't be giving you this expression. Either they will give you min terms also. Okay, min terms they might give you. So now if we see, so first search for a group of 16. You can see there is no group of 16. Next, you need to search for group of 8. I can see there is one group of 8 over here. This is one group of 8. Any other alternative group of 8 I can make? No, I cannot make a group of 8. Now next is what? Group of 4. So I can make one group of 4 like this. Now don't think that we can make one more group of 4 like this. No, this is wrong, because this whole group has already been covered in group of 8. So you don't need to make group of 4 in this over here like this. Okay, because all the ones have been already covered in this group of 8. So not required. This is one more. Now any other options or alternative for this one? No. Now one more group of 4 I can make. It is like this one, this, this and this. So you need to write what? You need to write the min terms for this one. So if I write for this group of 8, you can see only thing common is what? Y. So this is Y. Next, if for this one I write this group of 4, so you can see X is common and even Z is common, so XZ. So first is Y, then is XZ, and for this 4 corner group of 4s, what we have common? So W is not common, X complement is common, and out of YZ what is common? Z complement is common. So which option do we see? Option D. Option D is your correct. How many of you got option D? Chetan, Srihari, Chetan. Anyone got option D as your answer? No one got. It's okay. So such kind of questions might be asked in HAL, and trust me, in HAL from digital electronics, most of the question if asked, it will be from this chapter 1 only. Okay, because this has most number of theory and it has your easy questions, and in HAL there will be easy questions, there will not be tough questions. Okay, there will not be any tough question. Okay, fine. So now let us start with combinational circuit. So let me ask you, what do we mean by combination circuit? What do we mean by combinational circuit? Can anyone tell me? Srihari, you want to say? Chetan, you want to say? What do we mean by combination circuit? So any circuit whose output depends on the present input is known as combinational circuit. Okay, where we use multiple gates to actually generate output is known as combinational circuit. Now you might ask me, sir, is this a combinational circuit? No, this is a single gate. This is not a combination circuit. But if I combine few more gates with it, like this one, so this will be a combination circuit. So combination circuit, basically we combine one or more than one gates to make a circuit whose output depends on the present input condition. Such kind of circuit is known as combinational circuit. Now the first combination circuit that we have is what? It is your half adder. So from here, most of the time I guess that only theoretical questions will be asked. Okay, theoretical questions will be asked. So the first component is what? Half adder. So half adder, it is your combination circuit which adds two 1-bit number. Okay, it adds two 1-bit number. It has basically two outputs, sum and carry. So here these are your input and these are your output. So this will be sum, this will be carry. So you can see what? If A is 0, B is 0, if we add this to, sum will be 0, carry will be 0. For 0, 1, sum will be 1, carry will be 0. For 1, 0, sum will be 1, carry will be 0. When A and B, both of them are 1, sum will be 0, carry will be 1. So basically here what we are doing, we are adding two 1-bit binary number. Okay. So if we add 1 and 1, so this will be 0, carry will be 1. So that is what I have done. Okay. So basically we are adding two binary bit number. See, Boolean expression 1 plus 1 is 1. So this is Boolean algebra. And this is normal arithmetic. Okay, binary arithmetic we are doing. Okay, fine. So now we have what? Sum and carry. Now if you want to write the expression for sum, you can see what? That if you want to write, so sum is equal to 1 when A equal to 0, B equal to 1, or A equal to 1, B equal to 0, or you can simply write it as A complement B or A B complement. So this is what? A XOR B. And carry is what? Carry is basically 1 when AB both of them are 1. So this is your expression for carry. Now if you want to add B plus A, this will be also same. It won't matter. Okay, this will remain the same whether you do A plus B or B plus A. Okay, so this is your circuit diagram for your half adder. You can see this will be A XOR B, which is your sum, and this is your carry, which is AB. Okay, so this is your carry. So this is your circuit diagram for a half adder. Now, okay, so I have directly written, I won't be drawing. So how many NAND gate are required for constructing half adder? Can you tell this? So it will be 5. Okay, 5. And NOR gate, it will be also 5. So for constructing a half adder, 5 NAND gate and 5 NOR gate will be required for constructing half adder. Okay, so this you need to memorize, or you can even draw the circuit yourself. Now the next is what? Next is your full adder. So full adder is what? Suppose in the last case, if I want to add 2-bit number, okay, 2-bit number. So one of the number is like this, another is this. So you can see what? 1 plus 1 will be 0. Carry is 1. Now where will I add this carry? So this is taken care by full adder. In full adder, basically what we do, we have already two numbers along with the input carry. We have input carry over here. So basically a full adder is a combinational circuit which is used to add two 1-bit number which is used to add two 1-bit number and an input carry. Okay, two 1-bit number and an input carry. So this is known as what? This is known as your full adder. So in full adder, if you see, what will be the sum and what will be the carry? All the combinations can be like this. Okay, so here sum will be 0, even here also sum will be 0, sorry, sum will be 1, here 1, here sum will be 0, C out will be 1. I should have written carry also simultaneously. Here sum will be 1, carry will be 0. Over here sum will be 0, carry will be 1. Here sum will be 0, carry will be 1. Here sum will be also 1 and carry will be also 1. Okay. So now if I want to write what will be sum, so can you tell me what will be sum directly without even making the K map? See, you can calculate K map also or this sum. Okay, so over here you can see 1, 2 and 4, 1, 2 and 4 and 7. So already told you, whenever such kind of K map we have, so this is basically XOR. So this will be A XOR B XOR C in. Okay, A XOR B XOR C in, this we will have. And for C out, what will be the expression for C out? Can you calculate it yourself? C out. So if you make the K map, so here we have 3, 5, 6, 7. So 3, 5, 6, 7. So this 3 we will have. So A, B, C in. So for this group 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So here A is common. Okay, so A, and out of B and C, what is common in this group? So in this group you can see C in is common. A, C in. In this group again A is common in this group, I am telling. And out of B and C in, what is common? So B is common. And the last is this group, so that will be B, C in. Okay. So this is your what? This is your C out, expression for C out. So they might ask you directly what is the expression for S and C out directly. Okay. So HAL paper, there was one question last time they had asked what is basically A minus B. Okay, so half subtractor. They asked what is the expression for half subtractor. So borrow and carry, sorry, difference and borrow they had asked. So we are going to see in half subtractor also. Okay, first tell me if this is clear or not. Is this clear? Any doubts? See, one more thing I should have told you. See, so C out, what did we get? A plus B, C in plus AB. Okay, okay, we got this. One more thing we should have seen, that basically if you expand this, okay, if you expand this, you might be also getting, okay, so first let me make you understand over here. So a full adder is constructed using two half adder. Okay, we have two half adders and we construct a full adder using two half adder. Look over here. So we have this one half adder 1 and half adder 2. So the input of this half adder 1 is what? AB. So this is what? This is your carry and this is your sum. So that is A XOR B. Okay. So this A XOR B is coming over here and this Cin is coming. So this is the overall sum of the circuit. That is what? A XOR B XOR Cin. Now look at Cout. What do we get the Cout? So Cout is what? It will be AB, because this AB is coming from here. Along with that, we have A XOR B Cin. So this is also very important, that Cout, it can be written as A XOR B Cin plus AB. So these two are equivalent. Okay, these two are equivalent. Remember this. Is this clear? Is this clear? So you can solve it. Even this one, if you solve, you will be getting the same kind of K map. Same kind of K map. Any doubts? Srihari, Chetan?
No, no, no.
Okay. So I want to ask Srihari and Chetan, both of you, how is your preparation going on for HL? So have you guys given GATE this year? Anyone? No one has given GATE exam this year? It's okay. So now you need to remember this also. Full adder can be constructed using two half adder and one OR gate, two half adder, one OR gate, and the number of NAND or NOR gate required for constructing full adder is 9. For constructing half adder, it is 5. Okay. So this you need to remember. So this type of question won't be asked in GATE exam, but it might be asked in your HL exam. Now the next is half subtractor. So what do we mean by half subtractor? Half subtractor, basically if we subtract two one bit binary numbers, so we get usually difference and borrow. Okay, so that is known as your half subtractor. So here I will be doing A minus B. Okay, A minus B. So difference is denoted by D and borrow is defined by B. 0 minus 0, difference will be 0, borrow is 0. 0 minus 1, difference is 1, borrow is 1. 1 minus 0, difference is 1, borrow is 0. 1 minus 1, that is 0. So this will be also 0. So now if I want to write difference, okay, if I want to write difference, so what will be? So difference is equal to A, again it will be A XOR B. Look, it is A XOR B only. Okay, it is A XOR B. But borrow will be what? Borrow, if you see, it is coming at this place. So that is A complement B when it is A minus B. Now I want you to tell me what will be difference and borrow when we do B minus A. Tell me very quickly. What will be the difference and borrow if we do B minus A?
B X or B and B bar I.
Pardon, I couldn't hear you.
B bar I.
B bar A. Very good. So it will be B bar A. So if you see, wait a minute. So yes, I wanted to check if someone was waiting in the lobby or not. So if you do b minus a, okay, so difference will remain the same. So this will be 0, this will be also, sorry, this will be over here, this will be what? This will be 1, and borrow will be also 1. Here it will be 1 0, and here it will be 0. So difference will be same. But look at borrow. So borrow is what? It will be b complement a. Okay, b complement a, or you can even write it as a complement b. Okay, sorry, a b complement. Okay, a b complement you need to write. So this is what, this is very important, that borrow is different when you do a minus b and b minus a. So whenever in question, if it is asked a is subtracted from b or b is subtracted from a, so look very carefully and then write what is the borrow. If it is said a is subtracted from b, then you need to write borrow is b complement a. If it is said b is subtracted from a, then you need to write borrow as a complement b. Okay, so take care of this thing, because in lot of theoretical questions I have seen they have asked such kind of question and students they get confused. Now next is what? Full subtractor. Okay, full subtractor. So full subtractor, basically what we have, we usually have two 1-bit number along with one input borrow. Okay, we have one input borrow over here. So how do we do that? So look over here, basically we have a, b and borrow in along with difference and b out. I want you to very quickly find me what will be the difference and borrow. Is there was this one guy who had asked me for measurement notes. He is also not attending classes. Tell me very quickly what will be the difference. See, difference will still be the same. Okay, difference will be still the same. So this will be 0. Here it will be 1. B out will be also 1. Here if you check, so this will be, so here I am doing a minus b in. Okay, I am doing this, remember. So this will be 1, even this will be 1. Over here this will be what? Here you will have difference as 0 and borrow will be 1. Look very carefully. A minus b in. Okay, so a minus, for doing a minus b need to have one borrow. So I have taken borrow, and then b minus b in, this is 1 and 1. So this will be 0. Okay, here it will be 1, this will be 0. Here it will be 0, 0. Here it will be 0, 0. And here it will be what? Difference will be 1, and even borrow will be 1. Okay, difference will be 1, borrow will be 1. So now if you write difference, so difference once again if you solve, it will be a xor b xor B in. But what about B out? Can you tell me what will be B out? What will be B out? Very quickly tell me. B out, what will be B out? Quick. So what do you think will be B out? See, when you do A minus B, when you do A minus B, it will be A complement B plus B in plus B complement B in. So remember this. Whenever you do A minus B, so borrow will come only when A is 0, B is 1. Okay, either it will come when A is 0, B is 1, or when both B and B in is 1. Okay, when both B and B in is 1. Look at this place. So at these two places, this place, B and B in is 1. Okay, B and B in is 1, and even over here, B and B in is 1. And the last case is what? When B is 0 and B in is 1. So this is the case. This is the case. Okay, and this one means this over here. So B is 1 means both A is 0. This is A0, B1. So in both the cases, you can see this is A0, B1. This case I have. And over here again, we have what? B complement, B complement B in. B is 0, B in is 1. So this two cases, this one and this one. So I am marking this. This corresponds to this one. This two, B in. So this will be corresponding to this one. And this last one. Okay. So where is this? Even this one also. Okay. And this two cases, look, this case is corresponding to this one. Okay, so you need to be direct in writing like this. Okay, you need to be direct. Yes, tell me.
Sir, you marked 101 like a B bar B in. In the case of B bar B in,
B bar B in. Okay,
like you're told like 0 corresponds to
when
B.
B is 0, B in is 1, you will have carry. You will have carry. When B is 0, B in is 1. So where is B 0 and B in is 1? So at this place, even, okay, so I have made one mistake. Wait a minute. So at this place, I did not have borrow. Sorry. Wait. So B is 0, B in is 1. So where is this place? If you check in the borrow, so only in this place. At this place you have. Okay. At this place you have what? B0, B in 1. Now next see B in. Whenever B is 1, B in is also 1. So at this place you have, even at this place you have. Okay. Now last is what? A complement B. So A0, B1. So A0, B1 you have at this place. Any other place? So all the other places have been covered. Okay. All the other places have been covered. So for this, you can see as these two groups are common. So this will combine to give this one. This one will be combined by this. And this B in bar, this will come from here. Is this okay? Tell me. And if you don't feel comfortable, very quickly draw this, draw the K-map, you will get the same thing. If you draw K-map, so if you are not comfortable writing like this, then it's okay. You draw K-map, it will take only 30 seconds more. But don't make mistake. Okay, so this is 1 2 3, 1 2 3, and this is 7. So now make the key map. If you draw, so this is one group, this is one more group, and this is one more group. So for this one it is B in. Okay, this group I have done. Now this group, if you want to see, so that will be A complement, and over here B in, A complement B in. Okay, and this group will be what? This will be A complement B. Okay, A complement B. Okay, B. Wait a minute. So I had actually made a mistake last time writing. So I had written B in over here. Okay. So let me check once again. So this is B in. Okay. This is A complement B in, and this is again A complement B. Okay, fine. So this is correct. For A minus B, this is correct. Okay. A minus B, this is correct. Is this clear? Now it is correct. That is why you people were getting confused that sir has written something wrong. Yes, I was wrong. So I had written over here, I guess. What had I written over here? Means
I
directly when I had
think
written, I
B
think
bar B B
B in I had written. Then I had
B
written
bar.
B bar B in. Okay, so
Yes,
that
yes,
was
yes.
the wrong. Okay, so that was wrong. So this is what? This is your full subtractor. Fine. Now next we have is multiplexer. So what do we mean by multiplexer? And where do we use multiplexer? Can you tell me? Anyone? Anyone want to say where do we use multiplexer?
Like if we have multiple options of inputs, we need to switch something at a time.
Okay. So multiplexer is basically what? It is a combination of circuit, combinational circuit, which accepts data through multiple line and passes all of them through one output line at a time. So if I want to just explain, so this is station A, B, C, D. Okay. So A needs to transmit from A to E, from A to F, A to G, and A to H. Similarly, B needs to transmit from B to E, B to F, B to G, B to H. Similarly, C also needs to do. Now, if we do one-to-one connection, it will be very haphazard. So what we do, we basically use the combination of multiplexer and demultiplexer. So what do we have over here? So look very carefully. So this is one 4 cross 1 multiplexer. And here we have demultiplexer. So multiplexer is what? Many to one, and demultiplexer is what? One to many. Okay, one to many. So this will be E, F, G, H. So now if I want to transmit from A to H, I can do so with the help of combinations of S1, S0, and over here also S1, S0. If S1, S0 over here is 0, 0, and over here if it is 1, 1, then A will be connected to H. Similarly, if I want to do what? B to E, so over here the combination should be what? 0 1 means I haven't described what is I. This means these are your input channels. So I haven't actually told, but I am just making you understand what is the basic principle of multiplexer. So in multiplexer, basically what we have, it is one to many to one, and in demultiplexer we have one to many. Okay. So in multiplexer, we have many input line and a single output line, and in demultiplexer, we have one input line, many output lines. Okay. So demultiplexer and multiplexer combinedly, they are used to do what? They are used to transmit data from one source to different sources, or even data from different sources, from different sources to different sources. Okay. So this is the basic motivation of your multiplexer. So now in multiplexer, we have input lines. So these are your input line, and we have selection lines. Okay. We have input line, we have selection lines, and we have output. Suppose if input lines are n, okay, if input lines are n, so selection line will be log 2 base n, or if you say selection lines are m, then input lines will be 2 to the power m. Okay. So with this we have different combinations like 2 cross 1. 2 cross 1 means what? There are two inputs and one selection line. Then we have, sorry, selection line I am telling. 2 cross 1 means one output. Then we have what? 4 cross 1. So in 4 cross 1, we have what? 4 input and one output. So selection lines will be what? It will be log base 2 4. Okay, log 4 base 2. So this will be what? This will be 2. So selection line will be 2. Then we have 8 cross 1. In 8 cross 1, we have 8 input and log 2 base 8. So that is 3. 3 selection lines we have. Okay, 3 selection lines we have. So like this, we have different multiplexer according to the number of inputs. Now let us see one by one at how 2 cross 1, 4 cross 1, 8 cross 1 mux are there. Okay. So this is your normal 2 cross 1 multiplexer. Now look very carefully. Whenever S0 is equal to 0, I0 will be selected. Okay, I0 will be selected and I0 will be connected to your Y. If S0 is equal to 1, then I1 will be connected to Y. So how can I write this? When I0, okay, so I should be writing it like this. See, when S0 is 0, Y will be equal to I0. When S0 is equal to 1, Y will be equal to I1. So Y you can write it like this: S0 complement I0 plus S1 I1. So this is the expression for Y. So Y is equal to what? S0 I1. When S0 is equal to 0, I0 will be selected. When S1 is equal to 1, then sorry, S0 only. S0 is equal to 1, I1 will be selected. Okay, is this clear? Tell me, anything you want to ask, Srihari?
Nothing, sir.
Anything? Okay. So, have you completed your BTech, Srihari?
Yes, yes.
Okay, fine, good. So this is what? This is your 2 cross 1 multiplexer. So next is what? Next we have is a 4 cross 1 multiplexer. So in 4x1 multiplexer, the number of inputs are 4 and selection lines are 2. See, always they will be telling you which is MSB and which is LSB. See, if nothing is mentioned, then selection S1 will be taken as MSB and S0 will be taken as LSB. So Y will be equal to, if selection line is 0, 0, if selection line both of them are 0, 0, then I0 will be connected to I0. If selection line is 0, 1, I1 will be connected to Y. If selection line is 1, 0, then I2 will be connected to Y. If selection line is 1, 1, then I3 will be connected to Y. So we can write it like this: S1, S0, I1 plus S1 okay. So this will be the expression of output for your 4x1 multiplexer. Okay, 4x1 multiplexer. Now similarly we can have 8x1, 16x1, 32x1. So few questions that are asked in HL kind of exam, PSU exams, it is what? Implementation of Boolean logic using multiplexers. So the first is what? We have a complement. So kindly implement it using a 2x1 mux. So I will be showing you one. So they will ask you question like this. Okay. So this is your selection line. This is Y. So this needs to be A complement. So input is given in the selection line. Now tell me what will be the combination of I0 and I1 so that I get complement. So that I get a complement over here. See, if we don't know how to solve this, first write the generalized expression. So y can be written as y is equal to what? It will be your S complement I0 plus what? S I1. Now what we require? We require y is equal to A complement. So you can see over here A is already given. So if I take I0 is equal to 1 and I1 is equal to 0, then what will I get? A complement into 1 plus S is what? S is A into I1. So I1 is 0. So you get what? You get A complement. So for this combination, you will be getting what? You will be getting an inverter. So this is implementation of inverter using 2x1 mux. Any doubt in this? Any doubt? Any doubt? Okay, fine. Next is what? We have to implement AND gate using 2x1 mux. Okay. So take any one of the following, either A you can take or B you can take in the selection line. So write the generalized expression. So that will be what? S complement I0 plus S I1. Now what you need? You require y is equal to A dot B. So how can we get this? How can we get this? Simple. Simply put 0 over here and B over here. So this will be what? A complement into I0 is 0, okay, plus S is what? A, and I1 is what? B. So you got what? You got Y is equal to AB. So for this type of combination, you can create what? You can make AND gate using a 2x1 multiplexer. Now next is very good. I want you to construct this yourself. Okay, after this we will take a break because we have class till 8 today. Sorry, till 7, I guess. 7 or 8, I don't know the time.
In the group, it is shown as 5 to 8.
Okay, 5 to 8. Okay, so we will take, break means like for 15-20 minutes we will take break, and again we will start.
Okay.
Solve this. So what should you put in I1 and I0? See, this is very good. Okay, this is very good. So look very carefully. You require A plus B. Okay, A plus B. Now what you can do, if you substitute over here B in this point and 1 over here, what will happen? Look. Okay, look. If you are not able to solve like this, there is one more thing that we can do. See, you have this and you have A plus B. Okay, so you can put the value, means you select one of the variable that you are giving to the selection line, that is A. So this will be A complement into I0 plus A I1. Now you need to compare. Okay, you need to compare. So look, with A there is I1 and over here it is 1. So obviously I1 is going to be 1. But what about over here? What over here? So with A naught, means A complement, you have I naught. So what can I place at the place of I naught? See, if you place B over here, then what will happen? This will be A complement B plus A. Now if we do distributive property, this will be A plus A complement and A plus B. So A plus A complement will be 1 and this will be AB. So you got the required result. Okay, you got the required result. Did we understand this, Srihari?
Yes, sir. Clear, clear.
Clear? So always remember, whenever this kind of thing is asked, you need to substitute and check what you require. Okay. So okay, let us take break for like 20 minutes. Okay. So
Okay.
okay. So let us resume then. So next we want to find what? A plus B means NOR operation we want to find. Okay. So how do we do it? Wait a minute. So you can do, okay. So you can even write it like A complement dot B complement. So simply if you put I naught is equal to B, okay, or you can put it like, okay, B complement let us put, and over here if we put 0, so look what will happen. So this will be so here let me put A. So A complement B complement plus A into 0. So this is A complement B complement, so that is A plus B. Okay. So now let me ask you one thing. How am I getting this B complement? How am I getting the B complement? So B complement we cannot get by this mux. Okay. So we need one more mux. One more multiplexer is required for getting this B complement. Why? Because here we always have normal output, normal variables. We never have complemented variables. For making a complemented variable, we require one inverter. And we have just now seen how to make inverter using a 2 cross 1 mux. So before this B complement, we had actually B, we converted to B complement with the help of inverter. So this function is implemented using one inverter or using two multiplexer, two cross one mux. It cannot be implemented using a single 2 cross 1 mux. Okay, so this is very important. Now next is what we need to implement, a means NAND operation. So how do we do it? So we can write it like A complement plus B complement. Okay, so we have this. Now what we can do, see, if I put 1 over here and B complement over here, what will I get? So this will be A complement into 1 plus A into I1 is B complement. So this will be what? A complement means like this. So distributive property once again. So A complement plus B complement and A complement plus A. So this will be A complement plus B complement. So that is equal to AB complement. Okay. So this is what? This is your NAND using 2 cross 1 mux. But here also you can see I require this B complement. So this B complement, it will be generated either using a NOT gate or using one more multiplexer. Okay, using one more multiplexer we can construct this. Okay, now next is what? A XOR B. So for this, what will be the input combination? Okay, so what will be the input combination over here? So simply you need to put B over here and B complement over here. Then you will get it, because Y is what? It is AB complement plus A complement B. So I naught should be what? I naught should be B and I1 should be B complement. So then we will get what? A complement B plus A B complement. Again, you can see for getting this B complement, we require either one NOT gate or one mux. So they might ask you, how many number of 2 cross 1 mux is required to construct A XOR B? So your answer should be what? It should be 2. 2 2 cross 1 mux are required for your construction of A XOR B. Now similarly for A XOR B, you will be again same thing. See, this is what y is equal to A, means you require this Boolean expression. Okay, so this will be what? This will be B complement, this will be B, then you will be getting what? Again this. Okay, so any doubts in this? Any doubts? Okay, so now let us see how many 4 cross 1 mux are required for construction of A XOR B. So can you do this, Srihari, on yourself? So do this by yourself. So now we have 4 cross 1 mux. Okay, 4 cross 1 mux.
So ground the first input and the last input, and in between we can connect to source 1.
Yes, very good. So basically, if you see, so if I put in the selection line my A and B, so Y will be what? Y will be equal to A complement B complement I naught plus A complement B I1 plus AB complement I2 plus AB I3. Now, what I require A XOR B. So that is A complement B plus AB complement. So simply, if I put I naught equal to 0 and I3 equal to 0 and I1, I2 as 1, so then what will I get? I will be getting A XOR B. Okay, I will be getting A XOR B. Similarly, for A XOR B, okay, for A XOR B, I can do it using 1 4 cross 1 mux. Okay, so means previously from this case onward, where from here, okay, from NOR operation, we required what? We required 2 mux, okay, 2 mux for construction of your this thing, what, for your construction of this Boolean logic. Now tell me how many 4 cross 1 mux is required for construction of NOR. So this is very important. So what we require? We require A plus B whole complement. So that is what? A complement dot B complement. So simply if I put 1 over here and remaining all zeros, okay, remaining all zeros, so I will be getting what? I will be getting this one only. Okay, so you can see any two variable function I can construct using what? I can construct using 4 cross 1 mux, a single 4 cross 1 mux. But all the two variables cannot be constructed by a single 2 cross 1 mux. A single 2 cross 1 mux cannot do. But if I take a 2 cross 1 mux and inverter, I can construct all two variable function. Okay, I can construct all the two variables. So this is very important. So for constructing your n variable Boolean expression, a single 2 to the power n plus 1 cross 1 mux can do it. Okay, a n variable Boolean expression can be implemented using a single 2 to the power n plus 1 mux. But if I want to implement it using 2 to the power n cross 1 mux, then I require an inverter, or this inverter can simply be replaced by one more mux. So that will be 2 to the power n plus 1 into 2, means 2 to the power n cross 1 mux will be required for your construction of n variable Boolean expression. So now let me ask you, if I have a 4 variable function, Boolean function, and if I want to implement it using a single mux, what should be the size of the mux? Can you tell me?
16 is to
No, I have written, I told a single mux. So a single mux, that will be what? Here we have 4 variables. So 2 to the power 4 plus 1 into 1. So 2 to the power 5 into 1. So that is what? 32 cross 1 mux will be able to implement it. Just like we have seen over here. Just like we saw that a two variable, okay, two variable. Sorry, have I made a mistake? So two variable. Okay, sorry. I have written the wrong thing. So this should be 2 to the power n. Yes, you were correct. So that will be 16 cross 1 mux. And this will be 2 to the power n minus 1. Okay. So I made a mistake. 2 to the power n minus 1. So for a 4 variable function, we require minimum 2 to the power 4 cross 1. So that is 16 cross 1 mux is required. So that is what I had proved just now in the last cases, that for all the variable, 2 variable function, Boolean function, I require a 4 cross 1 mux. Similarly, a 3 variable, if I want to implement it using a single mux, that will be done by a 2 to the power 3 cross 1 mux. That is 8 cross 1 mux will be able to implement all the 3 variable Boolean function. But if I want to implement it using a 4 cross 1 or 2 to the power 2 cross 1 mux, so we will be requiring one inverter to implement. Okay. So is this clear now? So you were correct. I told the wrong thing over here. Okay. Is this clear now?
clear.
Yes. So now tell me, how many 2 cross 1 mux is required to construct a 4 cross 1 mux? How many 2 cross 1 mux is required to, sorry, 4 cross 1 mux is required for construction of 2 cross 1 mux? Can you tell?
Three numbers are required.
Yes, it is 3. Okay, can you tell me, see, I haven't written, I have just marked both of them as S only. So I want to know, let me write it as SA and SP. So which of the selection line is MSB and which of them is LSB? Which is MSB, which is LSB? Can you tell? Out of SA and SB, which is MSB and which will be LSB? Can you tell, Shriyari?
SB is LSB.
SB is, you are telling LSB. No, SB will not be LSB. See, why? Because look at the mux. Okay,
Okay,
look at the
fine.
mux, which is controlling all other mux. Which mux do you think is controlling all other mux? SB or SA? See, SA means so even over here also. I should have marked SA over at this point. Okay.
Okay, okay. Both are shorted, right?
Yes, both are shorted. Both are shorted. So now tell me, which do you think, SA or SB? Which is LSB? Which is MSB? Tell me. Which do you think is LSB? Which is MSB?
The
See,
controlling is SA itself.
what? See, basically this needs to be acting as your, means for the control 4 cross 1, this should be I naught, this should be I2, this should be I3, and this should be I4. Okay, this should be I4. See, if you take SB as MSB, SA as LSB, so what will happen? This is 0 0 0 1 1 0 1 1. So when SB is 0, so SB 0 means what? This line is getting selected. And SA0. SA0 means what? See, this line will be activated. Only output coming through this line will be taken as input. So SA0 means what? SA0 means both of these lines are activated. This line also activated and even this line is activated. So this is coming from here and this I naught is connected over here. But this line is not activated. Only this part is activated. So this I naught will be connected directly to Y. Now look. So output will be what? It will be I naught. Now look, SB is 0. So now look, SB is 0, SA is 1. So SB 0, okay, SB 0 means what? Still this line is connected and SA is 1. So SA 1 means what? This is even connected over here and this one is connected over here. But this line is not activated. Only this line has been activated. So I1 will pass. Now look, when SB is 1, SA is 0. So SB 1 means what? This line is getting activated now. Okay, this line is activated. This is not active. Okay, this line is active. SB1, SA0. So SA0 means what? From here, this line is active, but this line further it is not active. And over here, this line is activated. So this will get connected directly to I1. So this will be I0, but this I0 I have actually named it as I3. Similarly, this will be I4. So remember always the mux, the selection line of the mux that controls the maximum output, or sorry, the selection line or the mux that controls the maximum number of mux, it is your MSB. So look over here, this mux is controlling all the two mux. So that is why this mux is MSB and these two are LSB. Okay, this selection line is LSB. So here you can see for constructing a 4 cross 1 mux using 2 mux, 2 cross 1 mux, we required 3. Now similarly, if I ask you for 8 cross 1 mux, how many 2 cross 1 mux do we require? Very quickly tell me the answer. How many? You can tell the answer in like 2 minutes.
Seven.
7. Okay. So let us see. Now I am not going to draw. There is one shortcut trick. See, it is 8. So divide it by 2. So that will be what? 4. So next, divide this 4 by 2. So that is 2. Now next, divide this 2 by 2. So this is 1. So now add all this. So this will be what? 4, 2, 1. So that is 7. Similarly, for 16 cross 1 marks, if you see, so 16 divided by 2, that is 8. So 8 divided by 2, so that is 4. 4 divided by 2, that is 2. Quotient is 2. And 2 divided by 2, quotient is 1. So 8 plus 4, 12, 14, 15. So 15 you are going to require. Okay. Now if I ask you 16 cross 1 mux using minimum number of 4 cross 1 mux and okay, so I should be writing it like 8 cross 1 mux and 4 cross 1 mux and 2 cross 1 mux. So what will you say?
So 3.
3. Look how we do it. So 16, first select the maximum biggest mux that has been given. So that is 8. So 8 divided by 16 is what? That is 2. Quotient is 2. Now you cannot make a 2 means a 4. You cannot take a 4 cross 1 mux because you are getting 2. So now you need to take what? You need to take one 2 cross 1 mux. So you can see 1. So minimum number of mux will be what? A 2 8 cross 1 mux and a single 2 cross 1 mux. So such kind of question might also be asked in your exam. Okay. So like last, if I want to construct a 32 cross 1 mux using 8 cross 1, 4 cross 1 and 2 cross 1. So what will you say? Again select the maximum mux that is given. So that is 8, 4. Now I can make 1 means what? I can simply take 1 4 cross 1 mux and I will get. So here you can see 4 8 cross 1 mux is required and a single 4 cross 1 mux is required for minimum number of mux that is required to construct a 32 cross 1 mux. Okay. So like this we solve question of multiplexer. So now I have few questions over here. So let us try to solve one by one. So when two 16 input multiplexer drive a 2 input mux, what is the result? So can you tell what will be the answer?
32 inputs, sir.
32 input. Very good. So it is given two 16 cross 1 mux okay, 2 16 cross 1 mux. That means here we have 4 selection lines. So I am not drawing them. I am just making like this. So basically it is driving what? Two 16 input multiplexer drive a 2 input mux. So just now we saw a 32 cross 1 mux using 16 cross 1, 8 cross 1, 2 cross 1. So this is basically what? If you see, so this will be from here, How many selection lines do we have? We have 4, and from here we will have 1. So 5. In total, 5 selection lines. So that means what? Okay, let me ask you one more thing over here. See, selection lines will be like S3, S2, S1, S0, and over here, let me write it as S0 dash. Okay. So what will be the order in which the selection line will be written? Can you tell me? Order. So this will be a 32 input mux, but I want to know what will be the selection line order.
S0 bar, S3, S2, S1, S0.
Yes, very
S0
good.
bar is MSB.
This is the correct answer. Okay, so this is the correct answer. So this, I told you what, the mux that drives your maximum number of mux, that selection line will be your MSB. So you can see this mux is actually driving this too. So S0 will be MSB, and over here S3 is MSB. So obviously in the subsequent cases S3 will be taken as MSB, and your selection line will be like this. Okay, so D is your correct answer. So this question, tell me, what will be the answer for this question?
One, two,
Option
and
D,
two.
sir.
Option D you are telling. So which of the following circuit come under class of combination circuit? So full adder is a combination circuit. Full subtractor is a combination circuit. Half adder is a combinational circuit. Okay, JK flip flop and counters we haven't studied at the moment. So they are basically sequential circuit. In the next chapter we are going to see. So option D is your correct answer. Okay. So now this question, tell me what will be the answer. Answers? So
So
simply
one
it will be
option A, sir.
okay. Now look one thing. Here it is given a 4 cross 1 mux is used to implement a 3 input Boolean function as shown in the figure. The Boolean function FABC is implemented as. So it is given over here A is MSB, C is LSB. Okay, it is already defined. But look, the function that we are getting from solving, it is looking like this. So let us rearrange. So this will be A, B complement, C complement plus A complement, B complement, C, and this is what? This is BC complement. So this corresponds to what? 100. This corresponds to 001, and this corresponds to what? It corresponds to 111 and 0. Sorry, it is B complement. Sorry, BC complement. So this corresponds to what? 110 or 010. So this is what? This is 4162. So your minterm numbers are what? 1246. So which option do we see? Option A. Okay, option A we see. Now next is this. Okay, so we haven't done comparator yet. So this question, solve it. See, by looking at the option, you can see X is MSB and Z is LSB. Okay. So in that format only you need to write your
So B,
answer.
sir.
B. Okay, look. So F you can write directly how? So if it is Z complement, look very carefully. If it is Z complement, so this line will be getting selected. Okay, so open your bracket. So if this line has to be get selected, so write what will be the output of this mux. So that will be, if it is X complement, then this will be selected. So Y, okay, Y is over here. So if it is X complement, the 0th line will be selected. So Y plus. If it is X, then this will be 0. Okay, plus. Now again come back over here. If it is normal Z, if it is normal Z, then this line will be getting selected. Okay, this line will be getting selected. But here in this path, you can see there is one NOT gate. So simply whatever we have got over here, just complement it. Okay, so if you solve this, this will be what? X complement Y, Z complement plus Z. This will be what? X plus Y complement, or if you write it, so this will be XZ plus X, sorry, Z Y complement Z plus X complement Y Z. So which option do we see? XZ is present over here, Y complement Z over here. So over here X comp. Okay, so option B is your correct. Okay, option B is your correct answer.
So here
Now, yes, tell.
should be MSB, right, sir? Like
Which one?
Z should be the MSB, right? As previously
Pardon?
said.
I can't hear you. I can't hear you. Tell again.
Sir, we talked earlier about the selection line.
Yes.
Lines.
So according to selection line, this will be MSB. Okay, this will be MSB. This will be LSB. But in the question, you can see the option has been rearranged like X, Y, Z. So that is why we are taking it like this. Okay, but practically if nothing was given, then you need to consider this Z as your MSB and X as your LSB. And always remember, they will give you the order. Okay, they will give you the order, so no need to worry. Is that clear?
Clear.
So now solve this. See, directly you need to, so this E means enable. Okay, so whenever this enable input is here, so this is a normal enable. So normal enable, this whole mux will work when enable input is 1, and if enable input is 0, mux will not work. Okay, mux will not work. So if over here this enable was 0, whatever input you had, output will be always 0. But here you can see it is always connected to 1. Now one more way this could have been written, if there was a bubble over here, okay, bubble, or on top of this E there was a bar, so that means that is it is what? That means it is enable low. This is known as enable high.
Option D, sir.
And this, yes, okay, so option D you are telling. And this E equal to 0, for which mux work, and E complement if it is 1, mux does not work. So this is enable low. Okay, enable low. So in enable low, whenever your input to enable is 0, at that time only mux will work. Okay, so now let us solve this question. So directly if we see, so here enable is high, so I need to calculate this F. So first of all, F we can see it is equal to Y naught plus B complement. Okay, Y naught plus B complement. Now what is Y naught? If you want to calculate Y naught, so that will be what? A complement, B complement, C complement 1. Next will be 0. So I am not writing the terms of 0. I am not writing. Okay. So this will be what? A complement, B, C complement. For this one, we have written this one. This will be what? 4 and 6 we have. Okay. So this will be A, B complement, C complement plus A, B, C complement plus B complement. Okay, fine. So we have this. Now, what we can do, let us rearrange this. Okay, let us rearrange, or you can even draw the K map. It is up to you, whatever you want to do. So even K map will be easier over here to do. See, even directly without writing this, you could have made the K map and solved the question. It depends how good you are. Okay, so this is 0, this is 2, this is 4, and this is 6, and we have B complement. So B complement means what? All the places where B is 0. So here B is 0, even here B is 0. So all these places needs to be filled. So now you can see what? This is one group of 4 that I can make. Another is this group of 4 I can make. So this will be what? Over here we have B complement common, and in this group what do we have? So A is not common, so here C complement. So B complement plus C complement. So none of the options you can see is directly written. Option D, we can get it using your De Morgan's rule. So option D is correct. Okay. So now this question, okay, so this is 3x8 decoder. Okay, this Demux, can we solve it? See, I haven't told you what is a Demux. Okay, Demux. So let me just tell you that. So basically a Demux has a single input and multiple output. Okay. Okay. So this is your input and this is your output and this is your selection line. So whenever selection line is your complemented, at that time O0 will be selected, output this one, or when selection is normal, okay, normal, so then O1 will be selected. So this is your Demux. Similarly, you can have even 4x1 Demux, okay, sorry, 1x4 Demux, 1x8 Demux. So simple thing, just the opposite of multiplexer. So now tell me what will be the answer over here.
One second, sir.
So
Can I
half a
see the
done.
last slide once again?
Yes. Done?
Done, sir.
Okay, so what answer are we getting for this one? So in the next class, I am going to bring some delay questions also related to mux and all the gates, because that is important. Okay.
Okay, sir.
So actually, we shouldn't write it like this because this is OR I have written. So O0 will be equal to S complement if I write it I. So S complement I and O1 will be equal to Si. Okay, so this is the correct way of writing. Okay, so look over here. So the circuit shown can act as, so AB is input. If nothing is mentioned, so this will be MSB, this will be LSB. Okay, so this will be MSB, this will be LSB. So now look, if basically I and I2 it is odd, so I need to find X0 first. So X0 is what? It is I1 plus I2. What is I1? So they should have written output as O0, O1, O2, O3, but it's okay. I1 they have written. So I1 will be equal to what? AB means A complement B into 1, and I2 will be equal to what? It will be AB complement into 1. Okay. And so if I write this, this will be what? A complement B plus AB complement. So that is A XOR B. And Y naught is equal to what? Y naught is equal to I3. So I3 if I want to write, so that is AB into 1. So that you can see Y naught is equal to AB. So from the question, you can see what? That this is going to act as your what? It is going to act as your half adder. Okay, so option A is correct. Okay, so what about this one?
Single bit change between two successive code.
A gray code is a binary weighted code, arithmetic code which exhibits a single bit change between two successive code. So option C. If they had written reflective code, so then also you would have marked it. Okay, so code which exhibits a single bit change between two successive code. Already I have told you that
So
gray code. What? Pardon?
so actually, what's that reflective code?
So gray code is actually, it comes under your reflective code. Why? Because I told you. See, where is that? In regular class, I have told, I remember. See over here. So this is gray code. Okay, gray code. So now in gray code, look at this two term. Okay, look at this two term. So basically, you can just wrap this in a cylinder. So these two are consecutive terms, 0, 0, 0 and 1, 0, 0. Okay, these two are consecutive terms. Means if you write all this number on a rectangular piece of paper, and if you fold this end and make a cylinder by connecting this end to this end, then this two are your consecutive places. Means these are basically placed, what I should be saying is consecutive to one another. So that is why it is known as reflective code. You can see there is only one bit change between these two. Okay, there is only one bit change between these two positions. Now don't say, sir, is there any relationship between these two? No, there is no relationship between these two. There is only relationship between these two ends. So that is why it is known as reflective code. Okay, reflective code. Is this clear?
Okay.
Okay, sorry, means I was telling something wrong. Look over here also, this 2-bit, this 2-bit, even there is only one bit change. Look at this two consecutive next to. So even here there is only one bit change, and this two obviously there is going to be one bit change. So if you just fold it on a piece of paper, Basically there is only one bit change to the number that is diagonally opposite to it. Are you understanding? So if you take a cylinder and if you write 0 0 0 to this end, opposite to it, it will be what? 1. Means opposite to its end, it will be what? It will be 1 0. It's very difficult actually. 1 0 0. Now suppose if you take this one, this number 0 0 1, so the opposite, diagonally opposite to it will be what? It will be 1 0 1. So here also you can see there is only one bit change in this position. Similarly in this 2, you can see there is only one bit change at this position. Okay, so this is what we meant by reflective code. Is this clear now?
Yes, sir. It's clear.
Okay, so we were solving questions. This one,
So 1, 3, and 4.
1 3 and 4 means option C. So what it is given, consider the following statement: a multiplexer selects one of the several input and transmit to a single output, correct? Routes the data from single input to one of many output, this is Demux. Converts parallel data to serial data, yes, very good. Input is many, output is single, so parallel to serial, this is also correct. Is a combinational circuit, so this is also correct. So option C is correct. Okay, next. So in the next class we are going to see all the ripple carry adder, this look ahead carry adder, all these things we are going to see. In today's session we are going to finish this much questions and encoder, decoder and comparator. Okay, so what about this one?
Option B, sir.
B you are telling. So which one of the following statement correctly defines the full adder? An adder circuit having two input used to add two binary digit, it produces their full adder. Okay, so having two input, so wrong. A full adder has three input. Having three input used to add two binary digit plus a carry, it produces their sum and output, so this is correct. What is our next option? Used in least significant position, no, this is wrong. Having two input to two output, wrong, so option B is correct. Very simple question. Okay, so now we have is comparator circuit. Okay, so what do we mean by a comparator circuit? So comparator, any doubts, anyone? Okay.
No.
No, sir.
Okay, no issue. So a comparator circuit is a combinational circuit which is actually used to compare two inputs, two binary inputs. Okay, so very simplest is what? One bit comparator. Now this type of questions also might be asked that what is the output sequence? Like they might ask you what is the output sequence for this one when A is greater than B. So now look very carefully. If suppose I have AB, so output can be three. Either A will be greater than B, A equal to B, or A less than B. So A can be, as this is a single bit number. Okay. So in this case, A equal to B. So that means this output will be 1. Rest all of the output is going to be 0. In this case, you can see A is greater than B. Sorry, A is less than B. Okay. So here this will be 1, remaining all 0. Here you can see A is 1, B is 0, so A is greater than B. In this case, you can see A is equal to B, so remaining are 0. So now if I want to write the Boolean expression for this one, this will be what? A B bar. This you can see, this is what? A XOR with B, X nor with B, and this will be what? This will be A complement B. Okay, this will be A complement B. Okay, fine. So this for a single bit is very easy. So this might not be asked. What if they ask you about 2-bit? So then can you quickly write what will be A greater than B? What will be the output for this expression? Output for A greater than B, output for A equal to B, and output for A less than B. I am giving you 30 seconds to write for this one. Can you write it? See, the most logical way to write will be, see, as this is 2-bit, so A will be actually what? A1 A0, and B will be what? It will be B1 B0. Now you might be wondering, you can write it like A1 A0, B1 B0, and then you are going to write all the combination like from 0 0 0 0 to 1 1 1 1, and you will have 3 cases of output where A is greater than B, A is equal to B, and A is less than B. Okay, and then you are going to fill 0 1 accordingly. So you can do this also, but it will take lot of time. So then what is the easy method? Can anyone tell me?
So if A greater than B, so two possible cases there is either A1 is greater than B1, or
Okay.
A1 and B1 are same, and A0 is greater than B0, means A0 is 1 and B0 is 0.
Okay, good. Okay, so you write. So you know, it's okay. Right now. So I am giving you 1 minute. Then I will do. So look, when A is greater than B, so there are two cases. Either A1 is greater than B1. Okay, that means what? Either A1 is looking so like this, 1 0. This is the case, means the number I will show. Or if A1 is equal to B1 and A1 A0 is greater than B0. So that means what? For this case, the number will look like this, either 1 1 and this is 0 1, or this is 1 0 and this is 0 1. Like this number can happen, or even 0 0. Okay, even 1 0 0 1. So there can be lot of cases, and in this place it can be 1 1 and this can be 1 0. Okay, this case, or it can be 0 0 and over here 0 1. Okay, sorry, 1 0. So these cases can happen. So how do we write it actually? So look, A1 greater than B1, that means A1 B1 complement. Why complement? Because this is binary number. So if A1 has to be greater than B1, so A1 needs to be 1 and B1 needs to be 0. So if I want to write it, I am writing it like this. Or corresponds to plus sign in Boolean. A1 equal to B1. Now here this is basically equality. Either A1 can be 0, B1 can be 0, or it can be 1 1. Okay, so this is the cases. So this will be what? This will be corresponded by A1 XNOR B1, and means dot, A0 greater than B0. So this case means what? Either means this will be 1 0 only. So this will be A0 B0 complement. So now you can expand it and write however you want to write. Okay, so this will be the first case. Now next is what? A is equal to B. So if A is equal to B, that means what? A1 equal to B1 and A0 equal to B0. Okay, A1 equal to B1 and A0 equal to B0. So this, how can I write? So this will be A1 XNOR B1 dot A0 XNOR B0. Okay, very simple. Now similarly, you can even write for A less than B. So for A less than B, if A1 is less than B1, then A will be greater than, A will be less than B. Or if A1 equal to B1 and A0 less than B0. So if I want to write this, this will be A1 complement B1, A1 XNOR B1 dot A0 complement B0. Okay, so very quickly you can write it like this. Any doubt? Any doubt in this? So now
No doubt.
this question we can solve. Very simple. So here it is given what? Let x1, x0 and y1, y0 be unsigned 2-bit. Unsigned means what? That they are normal number, not in complemented form or in sign magnitude representation. The function f is equal to 1 if x greater than y and f is equal to 0. Otherwise, the minimized sum of expression for f is. So minimized SOP they are asking. So SOP means what? Whenever the function is 1, we get SOP. Okay, so x greater than y. So when is x greater than y? So we have just now written if x1 is greater than y1 or if x1 equal to y1 and x0 greater than y0, then x will be greater than y and f will be equal to 1. So this will be what? X1 y1 complement plus x1 x0 y1 x0 y0 complement. So here I need to open this. Okay. Okay.
Sir, y0 bar is missing
Where?
the second time.
Yes. So why not bar is missing? Okay. So now this question will be a little bit longer. Okay. So any ways that we can solve it directly over here? No, we cannot solve it directly. So we need to quickly make the K map. Okay, K map we need to make, or even if we look at the option x1, no, we cannot do anything. We require K map for this one. So x1 y1 x naught y naught. Okay. So such kind of question also will not be asked in HAL, okay, in PSU, because it will consume time. So they might ask you directly in terms of this one. So even I thought it will be like this, but here I can see that it will consume time. So x1, y1. So x1
So option
corresponds.
G, it is only matched for the first term. Rest of the other option.
Oh yes. Okay. So this is very good. So they have just kept only one. So this is very smart thing they have done. So only one of the option is matching for this one. You can see none of the others has this term. So obviously this term is required. Okay, this term is required. So this term cannot be missed anywhere. So only option D is remaining. So yes. So such kind. Okay. So I retract from my statement. Such kind of question can be asked. Even I did not pay attention to the options. Okay. So this is a good question.
So what if in the final reduction the x1 y1 will be absorbed or something happens?
No, 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 no. It will not be. See, whatever happens, do you agree to this or not? Tell me. This is your non-minimized expression. Okay, non-minimized. Now, what are the non-minimized term? You can see this one and this one. So when do we, in a 4 variable, listen very carefully, in a 4 variable K map, when do we get a 2 variable K map? Means a 2 variable minterm. What is the group size for a 2 variable minterm?
Quad.
What
Means a
is
quad. And these are what? These are your 4 variables. So that means a single term. So that means what? This is one, this is one. So this 2, if I make a group of 2, listen very carefully, you cannot minimize this anymore. Why? Because if this was getting minimized, so quad will get converted to a octet. So octet means what? There will be a single variable, either x1 or y1 or x1 complement, y1 complement, whatever might be present. A single variable would have been present. But in none of the option you can see a single variable is present first. So that means what? You can see there are 3 variables. So that means what? This 2 group is basically what? It is minimizing with this group to make what? A group of 2. Why? Because if group of 2 was not present, you can see over here this is becoming 2. So this cannot happen. This cannot happen. Why this cannot happen? Because here it is already quad, here it is a single term. So how can a quad make another quad with this one or this one? It cannot happen, because for making one more quad I require 2 more ones. See, listen very, means already I have a K map over here. See, this is, if I assume that this is the quad due to this x1 y1. Now if I take this 2 minterms, x1 y1 x0 y0 and x1 bar y1 not x0 y0, so if this 2 has a quad means one position somewhere like this, so this will make what? This will be one quad and this will be another quad. So then why is this term present? So this is already wrong. Okay, now look over here in this option. In this option, assume if there is one quad. Okay, there is one quad. So now tell me, if I am getting this expression, how can I get 2 more quads? 2 more quad, because this is the minimized, they have already written. This is the minimized sum of product. So how can I get 2 more quad from this 2 minterm? Because 2 minterms, this 2 minterm will give me only one, means 2 respective ones they will give me. So now tell me, how can I construct 2 more quads? I cannot make. So this option is also wrong. Okay, this option is also wrong. Now check for this one. This is already minimized and it has a quad. and this you can see is present over here. So this is not getting minimized. Only minimization is taking place into this one. Okay, but this term is not present over here because it is already minimized and this term is not present. So this is also wrong. So the only option remaining is this one, and this reduction is coming from this two terms. Okay, now tell me, is this clear what I tried to make you understand?
Clear, sir, very much.
Okay.
So,
So now the last topic that is left is decoder. So it's okay. So it's already 8. Okay. So decoder, it will take few minutes. So it's okay. So in the next class, we are going to see decoder and this chapter will be over. Okay. So we will start with the most important thing, that is your sequential circuit. Okay. So we will start with sequential circuit in the next class.
Thank you, sir.